Now for our very last example here in section 3.5, we're going to kind of give a little bit of motivation for why you might want to even take a second derivative. So we're going to think about a car. So here I have a car on the road. I'll try to draw a little car. Okay, not an artist. I'll try to draw a little car there. And let's say that at 0 seconds, so at the very, very starting point of my car driving on this road, it's gone 0 feet. So at 0 seconds, it's gone 0 feet. And let's say that I hit the gas pedal, so I'm going to start to move. And let's say that my velocity or speed, is what velocity kind of represents, this idea of speed. Let's say that my speed, I'm going to go 29 feet per second. Okay. There's this idea of my speed increasing. So let's say that at 1 second. So after 1 second, I drive my car and I'm here. After 1 second, let's say that I've gone 34 feet. So that's my position. That's how far I've traveled, 34 feet. My speed at this particular instant would be 38 feet per second. And we want to talk about the acceleration. So we want to know how fast the speed is changing. Okay, so we're given a function. I'm going to come back up here to the top. We're given a function s of t for all of these that gives position. So this is telling me how far I've moved. So it gives me the position of an object at any time. So here we have s equals 0 feet, and then we've gone 34 feet, and then here we've gone 74 feet, and then here we've gone 114 feet. So let's say right there. Okay, so it tells me how far I've traveled, so kind of like the distance. The velocity is telling me the rate of change. Remember, derivatives are rate of change. It's the rate of change with respect to position. So it's telling me how fast that I'm changing position. So the velocity here is 29 feet, so that's position, and tells me how fast that I'm doing that. So 29 feet per second. So this is how the rate of change with respect to position, so how fast I'm going. So here we have 38 feet. We're going 38 feet for every second that we're driving. And here at this instant, we're doing 41 feet for every second, and here 38 feet for every second. I want to know is how fast that I'm changing my speed. So acceleration is the rate of change with respect to velocity. So how fast is your speed changing? So not position, but how fast is the velocity changing? Okay, so this tells me I'm traveling 13 feet per second per second. Okay, so it tells me how fast that my speed is changing. Okay. There's one point here, it says 0 feet per second per second. So basically that's telling me that my speed is not changing. Or my velocity is not changing. So it's keeping steady. Basically almost like you, for that one instant when you take your foot right off the gas pedal. Okay. So think about the original function is giving us a position. The first derivative, in other words, though, is telling us the rate of change with position, so how fast or speed. The second derivative, then, that third function, is going to give us how fast our speed is changing, or in other words, the acceleration. Okay, so rate of change is what a derivative is, and we want to know how fast something is changing. We can take a derivative to discover how fast something is changing. And all of those are what we call instantaneous rates of change. Okay, so keep that in mind. So our problem here is asking us, if the distance s in feet covered by a car t seconds after starting is given by the following function. So this is what we call a position function. This is telling me the feet that I've gone, so feet that I've traveled. Okay, so it tells me how many feet I've traveled, and t represents the number of seconds. So between 0 and 6 seconds, this function tells me how far my car has traveled. It says find a general expression for the car's velocity and the acceleration at any time t. So velocity is asking me for the first derivative. Acceleration is asking me for the second derivative, so how fast my speed is changing. So let's go ahead and take the first derivative. The first derivative, now really nice, I've given you just a very straightforward function that we just have to use the power rule here to find that first derivative. So that would be negative 3t squared plus 12t plus 29. So I want to find the second derivative. So we're going to take the derivative again. Okay, remember this tells me speed or velocity, and this tells me acceleration. Okay. Take the derivative again. 3 times 2 is negative 6t plus 12, and then the derivative of 29 is 0. So there's my second derivative. Okay, so pretty easy. So here we're asked a question about our problem. It says, at what time t does the car begin to decelerate or decrease in speed? Okay, and that gives me a hint. The car begins to accelerate when the when the acceleration equals 0. So let's look at an example really quick up here. So let's go back up to our little diagram. Here our acceleration is pretty fast. We're increasing our speed by 12 feet per second. Here we're kind of slowing down a little bit. We have 6 feet per second. And then here it says we're not changing our speed at all. Our speed is not changing. Notice here our acceleration becomes negative, which means that we are decreasing our speed. That means our speed is going down. So let's look at our velocity, 38 feet per second. And then it says 41 feet per second, so we're getting faster. And then all of a sudden the velocity starts to come back down. So the velocity is increasing, and then here it starts to decrease. So our acceleration is telling us, okay, you're going faster, and then you level off. You stop going faster or slower, and then here your speed is going down. So we're decelerating. So this is decelerating. Okay. So here, at what point do you start to decelerate? Well, it says you start to decelerate when your acceleration is 0. So that's our little hint. So what we're going to do is we're going to take our second derivative, the acceleration equation, and we are going to say, when does this equal 0? What we want to know is, at what time does that begin? So we're going to do negative 6t plus 12 equals 0, and then we're going to solve for t. Okay, so we're going to say if our acceleration equals 0, at what time does this occur? So pretty easy equation to solve. I'm going to bring over the 12. It becomes a negative 12. I'm going to divide both sides by negative 6, and we get t equals positive 2. So when t equals 2 seconds, that is when our car begins to decelerate and we start to basically decrease in speed or slow down. Okay, so that's the very instant when deceleration begins.